Here is a problem related to some pulleys. And let's do a little bit of a review of mass moment of inertia. This time it's given to us, but most of the time in pulley problems or gear problems, the mass moment of inertia is given to you through the radius of gyration k. And this k value is going to be in units of length. So here in the English system, the mass moment of inertia is pound-feet second squared. If we look at the force equals mass times acceleration, we know we have pounds, we know we have slugs, and we have acceleration in feet per second squared. If we solve for slugs and see what units slugs are, those are going to be pound times seconds squared divided by feet. And when we're finding the moment of inertia, we multiply the mass times the radius of gyration for problems, again, like gears, because gears have teeth in them and you can't necessarily use the equation for a circle or a disc on a gear. These are for round circles and discs. A gear doesn't fit that category. So you're usually going to get a radius of gyration. And as we saw, we are going to be working with these pulley problems, pound feet times second squared. And that is going to be the units for mass moment of inertia. In the English system, if we have slugs, which are pounds second squared divided by feet, multiplied by k, which is going to be in units of feet. If it's given to you in inches and you are working with slugs, you have to turn that into feet. And so the foot cancels out and you're left with pounds second squared and feet. All right, so in this problem, we are just going to focus on the first part, determine the angular acceleration of each pulley. We've already done the angular velocity in other chapters, and so that really isn't something that we want to focus on here. We want to look at what's going on with the difference between if we just pull down on a rope versus if we have a mass at the end of the rope. So problem number one, if we're going to find alpha, we're going to sum the moments around the center of mass and set that equal to I bar alpha. We don't have the MAD in this because D goes to 0 when we're at the center of mass. So if we look at the moment, we're going with an R component in the negative direction of I, and that's going to be equal to 9 inches. And again, we've got to change that inches into feet. So we're going to have 9 over 12, and that's going to be our R component. That is, if you want to work in vectors, a minus I crossed with a minus J component of 160 pounds. That's the only thing creating a moment on this pulley. We set that equal to the I times the alpha. The I we're given as 15, and the alpha we need to find. If we solve this, we're going to end up with an alpha equal to 8 radians per second squared. and that's going to be going in the counterclockwise direction, which makes sense. If we pull down, it's going to spin that direction. What is different when we look at the mass? If we sum moments around G for pulley number 2, we are going to deal with a value for this mass times acceleration times distance, because we're concerned about this mass right here, and it takes time for the block to overcome inertia. And I often show a video to my physical science students with a basketball and a bowling ball, and they both hit the ground at the same time because they're both acted on by gravity. And the bowling ball takes longer to fall than the basketball and start to get going. But once it's going, it is going to hit the ground at the same time as the basketball. So what are we looking at here? We're going to have, again, a 9/12, and that is going to be feet in the I direction. Our R component hasn't changed any. And that's going to be crossed with 160 pounds, also in the minus J direction. And we're going to set that equal to the same I bar, which we've been given. We're going to find a new alpha, and then we're going to figure out what do we do with this MAD this time. All right. So we're going to use the mass of this weight, 160, and divide it by 32.2 to get it into slugs. And then we're going to look at this in the sense of a tangential velocity or an acceleration, AT, where AT is equal to alpha R. And so we're focused on the fact that we have mass at a distance away from the center. So that mass is going to be this R times alpha, 9 divided by 12 alpha. So that's this part. And it is that distance away because we're looking for the line of action for that acceleration. So just like summing moments, and it's going to be 9/12. If we solve for alpha here, alpha is going to be equal to 6.74 radians per second squared. And once again, it is going to be in the plus k direction, counterclockwise. Okay, let's look at just finishing up 3 and 4. 3, if we have a 460 pound weight on that side, and we have a 300 pound weight on that side, this is where the force is acting in terms of our acceleration. Remember, force is equal to mass times acceleration, so we have mass down here, and it's accelerating because these are not balanced. So summing moments around the center of mass is going to be equal to I bar alpha plus MAD for the 460 pound weight and plus MAD for the 300 pound weight. Let's look at summing the moments. So on the left hand, we're going to have 460 multiplied by the same R component. I'm doing it in scalar this time. And that is going to be a plus K component once you do the cross product. The other side is going to be a minus. So 300 times the R component in feet. And that's a minus K component. Plus 15 times alpha. And now we're going to put the 460 for the mass divided by the acceleration of gravity. And we are now in slugs. And we're going to have the same sort of tangential equation that we have to deal with here. 9, 12 alpha at a distance of 9 over 12. And plus 300 divided by 32.2. And this is going to be a plus K component. And this 9 over 12 alpha. And 9 over 12. Let's see. We are going to have the acceleration. This is going to be pulling down. So we are going to have an acceleration in the tangential direction going down, but this is heavier. So this is actually going to be lifting up like that and spinning in that direction. Otherwise, if they were balanced, they wouldn't move, but we're in dynamics, and so they are moving, and the 300 is going to be moving up. So that means our R cross our alpha, or our force, is going to be another plus K component, because both of these are going to have to be going in the counterclockwise direction, and the 460 is going to win. Okay, if we solve all of this for the unknown of alpha, alpha for part 3 is going to be equal to 4.24 radians per second squared, again in the counterclockwise direction. And then what happens if we work with a longer radius? That is the question for the last problem. 80 pounds at a distance of 18 inches, twice as much, but half the weight. So we're just looking at comparing these alphas. Summing moments at G is equal to I bar G alpha plus M A T. So we're going to have our 80 times 18 divided by 12 for the radius, 15 alpha plus the weight again, 80 divided by 32.2. And again, the acceleration in the tangential direction, because it does have a normal component, that's another thing, but the normal acceleration is canceling out when we are looking at summing moments at the center of gravity, but the tangential for that mass does not. So let's go ahead and put 18 over 12 alpha at a distance of 18 over 12 away. And if we solve for our value of alpha for the last one, we're going to find that this is 5.828 radians per second squared. So let's analyze what we have. We have half the mass and twice the moment arm of number. And so we're going to be almost half the alpha, but not quite. We have an alpha that's less than this alpha, even though we have the same force pulling down, we have mass that is less because it takes time for the block to overcome inertia. And so we have 6.74 here instead of the 8. And right here, this one is just balancing out, where you can see that we need to have this as a plus k component, and that's due to the acceleration having to go up when we have 300 pounds going down. All right, so that's that problem. Pause.